All right, in this video, we are going to move into section 3.8, which is titled Implicit Differentiation. So like I mentioned in the last video, we have one new derivative technique we need to learn in order to do the last section in 3.9, and that's what we're going to cover today. So let's learn about what implicit differentiation is. So to differentiate implicitly, we're going to see an issue where up until this point, we have always taken the derivative of y equals a function of x. Well, in this section, we're not going to have that anymore. We're going to have random equations where x's and y's are all over the place, and we still need to be able to take the derivative. So here's kind of a guideline of how we're going to do this today. So step number one, we are going to differentiate both sides of the equation with respect to x, or whatever variable you're differentiating with respect to. I threw that extra little note in there because in the next section, we're going to differentiate with respect to t sometimes, which will affect how we label stuff. So when you differentiate, you apply the rules of differentiation as necessary. Anytime an expression involving a y is differentiated, you will have to put a factor of dy dx onto that derivative. So let me say that again. When you take the derivative of a function involving y, you have to add a dy dx term. Once you go through all of that, you need to isolate every term that has a dy dx on one side of the equation. When you do this, you will be able to factor out the common dy dx, and then you will divide both sides of your equation because your ultimate goal in these problems today is to isolate the dy dx term. And as you should remember from Leibniz notation, dy dx is the derivative function that we're trying to find. So will all these techniques be necessary every time? No, some of them will be able to skip depending on the problem, but this gives us kind of a little bit of a structure of what to work through as we take the derivative implicitly. So a lot of this section is just going to be me showing you how to do derivatives implicitly. So let's work through a bunch of examples. So example number one, differentiate implicitly to find dy dx if y cubed is equal to x to the fifth. So essentially how implicit differentiation works now that we have our first problem is you don't move anything around. All you're going to do is you're going to take the derivative of every term you see exactly as it sits. So for example, the derivative of y cubed would be 3y squared. But from those instructions I gave you, anytime you take the derivative of a y term, you have to add a dy dx term onto the end of it. We'll bring down our equal sign, and the derivative of x to the fifth is 5x to the fourth. Once you take the derivative, your goal is to isolate that dy dx term. So I'm now going to divide both sides by 3y squared. This cancels, and you can say that dy dx is equal to 5x to the fourth divided by 3y squared. And this will be the derivative of your implicit function. One big thing you will notice today is that the derivatives of these functions will have not only x's like we're used to, but they'll also have y's in them as well. So it is okay to have x's and y's in your final derivative when you do implicit differentiation. All right, so let's run through some more. How about example number two? If the equation is 2xy plus 3 equals 0, find the derivative implicitly. Now, the difference on this one is that since we're taking derivatives of every letter, we have to note that when I say 2xy, this is the same thing calculus-wise as saying 2x times y, which means that when you take the derivative of this, we haven't done this in a little bit, you will have to do the product rule to find the derivative of 2x times y. So if I let 2x be my f function and I let y be my g function, remember that the product rule is defined as fg prime plus gf prime. If I follow this rule, doing my implicit derivative of the product rule, I'll take my f, which is 2x, multiplied by the derivative of g. Now, the derivative of y is just 1, but since it's a y derivative, you have to add a dy dx term onto it, plus your g function, which is y, times the derivative of f, which is 2. Moving on to the next term, the derivative of 3 is just 0, so that goes away. I'll bring down my equal sign, and the derivative of 0 is also 0. Cleaning this up, we can simplify this into 2x times dy dx plus 2y equals 0. And then if we try to get the dy dx by itself, I'm going to subtract 2y from both sides. This is going to give me 2x times dy dx is equal to negative 2y. And then if I divide both sides by 2x, this cancels. And what you will notice is that sometimes when we do these implicit derivatives, some terms cancel. So when you have negative 2y divided by 2x, I notice that these 2's will cancel, which leaves me with a final derivative of just negative y divided by x. So dy dx in this problem is negative y divided by x. All right, let's continue this trend. So how about number 3? Find the derivative implicitly of e to the 3y plus 4x cubed is equal to 2 times the natural log of y. So once again, I need to take the derivative from left to right on this function. So recalling what the derivatives of e's are. When you take the derivative of an exponential function, remember you take the derivative of the power, which is 3. Now, since that is a y function, I have to actually write it as 3 dy dx, and then you bring down your exponential function, which is e to the 3y. Plus, the derivative of 4x cubed is 12x squared equals 2, because it's just a constant. The derivative of the natural log of y is 1 over y. And since that is a y function, we have to put a dy dx on there. Now, if I clean this up a little bit, I could write this as 3e to the 3y dy dx plus 12x squared equals 2 divided by y times dy dx. Now, you need to get all the dy dx terms on the same side. We haven't done this yet. We've only ever had one. But when you've got multiple dy dx terms, you need to move them all to the same side. So I'm going to subtract the 3e to the 3y dy dx from both sides. That'll be the simplest thing to do. This cancels, and you're left with a 12x squared equals 2 over y dy dx minus 3e to the 3y dy dx. To make multiple dy dx terms into one, we're going to factor it out. So the 12x squared on the left is not going to change. On the right, if I factor the dy dx out, I'm left with a 2 over y minus 3e to the 3y. The last thing you have to do is to divide both sides by what's inside this parentheses. So that's the 2 over y minus 3e to the 3y. Now, what I notice here is that this cancels, and it doesn't look like anything's in common, so we should be done with this problem. I'll write my final answer up here at the top out of the way. So I can say that dy dx is going to equal 12x squared divided by 2 over y minus 3e to the 3y. This is the derivative of the original function. So a little bit more work involved on that one because we had multiple y terms. But like you can see, when you've got multiple dy dx terms, move them all to the same side, factor out the implicit term, and then solve for dy dx. Let's do another one. All right, so number 4, find the implicit derivative, or find dy dx implicitly, of x times y to the 5th plus 4x cubed y is equal to 7. Now, in this example, you're going to notice two things. Number 1, as we've talked about, this x times y to the 5th are being multiplied, so you will have to do the product rule, not only here, but you'll have to also do the product rule on the second term, because that's a 4x cubed times y. So both of these separately have to be done with the product rule. So once again, remember, the product rule is equal to fg prime plus gf prime. So let's do the product rule twice of each pair of functions. So starting with the first product rule, I would take f, which is x, times the derivative of g, which would be 5y to the 4th, times a dy dx term, plus your g term, which is, y to the 5th. Apologies for that. Let me erase that. Go away. There we go. Y to the 5th times the derivative of f, which is 1. That is the product rule of the first two terms. Then I bring down the plus sign, and now I have to do the product rule again for these second two terms. So I would take my f function again, which is 4x cubed, times the derivative of g, which is 1, dy dx, plus my g term, which is y, times the derivative of f, which is 12x squared. These second two terms is the product rule of the second pair of functions. This is equal to the derivative of 7, as we've seen a few times with constants, is still 0. If I were to clean all this up a little bit, let's see, that's 5xy to the 4th dy dx plus y to the 5th plus 4x cubed dy dx plus 12x squared y is equal to 0. Now, since everything is on the same side of the equation, remember, you're trying to isolate the dy dx's. So the next thing I'm going to do is I'm going to move these two terms that don't have a dy dx, I'm going to move those over to the right-hand side. And you're going to be left with 5xy to the 4th dy dx and plus 4x cubed dy dx left on the left-hand side. On the right, if I subtract both of these over, you'll have a negative y to the 5th minus 12x squared y. Then you have to factor out the implicit term. So that would be dy dx, and you would have 5xy to the 4th plus 4x cubed left over. The right-hand side for y'all is not going to change. And your last step here is to divide both sides by what's inside the parentheses. So I would divide both sides by 5xy to the 4th plus 4x cubed. If you take a look real quick, I know that this cancels. And looking at these four terms, it doesn't look like there's anything in common. So therefore, I can say that my final derivative is going to be negative y to the 5th minus 12x squared y over 5xy to the 4th plus 4x cubed. This is the derivative of the original expression. Once again, you got multiple dy dx terms again, so that's not different. Only difference on this one is you had to do the product rule twice for each pair of multiplied functions. All right, now that we've gotten down implicit differentiation, let's talk about how we can use this to do our tangent line problems that we did a lot of back in chapter 1. So we're going to do two of these together. Number 5 says, find dy dx given the equation 2x cubed plus 4y squared equals negative 12. Then I only want you to find the slope of the tangent line at the point -2, -1. All right, so first thing I'm going to do is I'm going to find dy dx. So we're going to take our derivative implicit. Derivative of 2x cubed is 6x squared. The derivative of 4y squared is 8y dy dx equals the derivative of -12 is 0. If you subtract the 6x squared over, you will have 8y dy dx equals -6x squared. And then if you divide both sides by 8y, this cancels, and you will notice that you can simplify this a little bit. The 6 and the 8 both share a 2 in common, so this simplifies into -3x squared divided by 4y. So that is the derivative of our function. The difference here is you now need to find the slope of the tangent line. Now, back when we did slope of a tangent line in chapter 1, you had to plug your x value into the derivative to get slope. The difference now is if you look at your derivative here, it has x's and y's in it. So using the point -2, -1, you need to plug both your x and your y into the derivative to find the slope of the tangent line. So our slope here is going to equal -3. If I plug the x in, that's -2 squared divided by 4 times my y value, which is -1. Then I'm going to clean this up. So this is -3 times 4 over 4 times -1. Well, very nicely, the 4's cancel here, and -3 divided by -1 is +3. And that would be the slope of your tangent line at the point -2, -1. It didn't ask for the entire line, so we're not going to find that here unless we have to. Most of the ones in this section just want you to practice finding the slope. Let's do another one just like that so you have a second one in your notes. So same instructions. Excuse me. Find dy dx given the equation 2x cubed y squared equals -18. Then I want you to find the slope of the tangent line at the point -1, 3. So first thing again, I need to find my derivative. You will notice for I think the third time today, you've got two functions of x and y being multiplied together. Since they are multiplied, you're going to have to once again do the product rule. So remember, product rule is fg prime plus gf prime. The good thing is you only got to do it once this time for this problem. So if I bring down my f function, that's 2x cubed times the derivative of g, which would be 2y dy dx, plus g, which is y squared, times the derivative of f, which is 6x squared, equals the derivative of -18 is 0. So I've got to get this dy dx by itself, so let's clean this up a bit. This would be 4x cubed y times dy dx plus 6x squared y squared equals 0. If I move the term that does not have the dy dx, so I'm moving the second term over, that would be 4x cubed dy dx equals -6x squared y squared. And then notice this time, if you divide both sides by 4x cubed y, that all cancels, and then you can simplify your derivative a little bit. If you notice, this y squared and this y both share a y in common, so this y goes away, and that's 1y. There are two x's in common, so this x squared goes away, and this is x to the first. And then both of your numbers share a 2 in common, so you can divide those by 2. When all is said and done, you should end up with a derivative of -3y over 2x. This is the derivative of your function. Just like earlier, since we have x's and y's in our derivative, I need to take x equals -1 and y equals 3 and plug those into my derivative to get the slope of the tangent line. So m would be -3 times my y, which is +3, over 2 times my x, which is -1. This would be -9 over -2, which double negatives cancel, and you get a slope of 9/2 for the slope of this tangent line. So just remember, the only difference at the end is after you find dy dx, you got to plug x and y both in. All right, and then last but not least, to kind of get us ready for what we're going to see in our next video in section 3.9, let's see if you can find dp dx given the following demand equations. So do note, the only difference I'm doing is changing the letters. There are no y's in these problems. I turned them into p's. So that means that when you take the implicit derivative of a p equation, you have to add a dp dx. The x's you'll treat the same way. So for the first one, I made up p squared plus p plus 2x equals 40. Find dp dx. Well, if I take the derivative exactly as this sits, the derivative of p squared would be 2p dp dx. The derivative of p is just 1 times dp dx. The derivative of 2x is 2 equals the derivative of 40 is 0. Cleaning this up, you should have, you should have 2p dp dx plus dp dx. Now this lonely 2 right here, I'm going to go ahead and move it over and make it a -2 because I need it to be by itself. I'm then going to factor the dp dx out of both terms, which leaves a 2p plus 1 left over. And then if I divide both sides by the 2p plus 1, I can say that dp dx is equal to -2 over 2p plus 1. And this is the derivative of your p function with respect to x. Now, just a coincidence here, we didn't actually end up with a x in our answer. That's just a lonely coincidence there. That's not a set reason why that happened. All right, and then one more problem for this video, number 8. Find dp dx for the equation x cubed times p squared has to equal 108. Well, for I think the 4th or 5th time today, you're starting to notice a trend with these implicit derivatives. These are two terms being multiplied together, so you're going to have to once again do the product rule of this derivative. So if I were to do the product rule of x cubed times p squared, this would be f, which is x cubed, times the derivative of p squared is 2p times dp dx, plus my g function, which is p squared, times the derivative of f, which is 3x squared, equals the derivative of 108, which is 0. Cleaning this up, you should get 2p x cubed dp dx plus 3p squared x squared equals 0. If I move this second term over to the right to isolate it, you should get 2p x cubed times dp dx equals -3p squared x squared. The last thing I'm going to do here is divide both sides by 2px cubed. And you're going to notice once again that there's a few things that cancel here. First off, I can cancel 1p off the top and the bottom, and I can cancel 2 x's off the top and the bottom. This allows me to write my simplified derivative as dp dx is equal to -3p on top And oops, that should actually be a 1 right here. We canceled 2 of those. So you end up with a 2x on the bottom. This would be your final derivative of p with respect to x. That ends the video for section 3.8. So in this video, remember we covered how to take the derivative implicitly. So we went through a bunch of examples. In the next video, good news, it's the last video for this class. 3.9 is the last section you have to learn. We're going to use this idea that we covered today, and we're going to look at the idea of related rates, which is word problems involving implicit differentiation.